So this is a discussion of velocity in one dimension. Average velocity is the change in position divided by the change in time. It's the rate of change in position. And so we write it this way. We say V average is equal to delta x over delta t, which is just the final position, the position at some time, minus the position at an earlier time, so the change in position, divided by the times corresponding to those two positions. So for example, if I had a little car and it started here at 10 meters, right, this is my x position in meters, and at a time of 1 second, I started my watch a second ago, say, it was at the 10 meter position, and then 3 seconds later, it was at the 25 meter position. I could say, well, at t1 equal 1 second, it was at position at 10 meters. 3 seconds later at t2 equals 4 seconds, it was at position x2 equals 25 meters. And then I can calculate the average velocity between those two positions. I would say the average velocity is the difference between the two positions, or the change in position, divided by the difference between the two times, or the change in time. And for this car, the change in position divided by the change in time would be 15 meters divided by 3 seconds, or 5 meters per second. So the average. So it turns out we can plot the position of the car versus time on a position versus time graph, and we can learn some interesting things doing that. And so that's what we're going to do. We're going to say, look, the car started at t1 is equal to 1 second, right here, and it was at position x1 is equal to 10 meters. And so I'm going to put a little dot on my graph, and I'm going to draw a little dotted line connecting those, so we know that at t1 it was at 1 second, and at x1 equals 10 meters. Similarly, I'm going to put an x2 by 25 meters, and that happens at t equals 4 seconds, and so I'm going to draw a little dot here, right, and I'm going to draw a little dotted line down to the 4 second mark, right. Similarly, I'm going to draw a horizontal dotted line here. And so if the car moved from 10 meters to 25 meters at a steady pace, right, it did that over those 3 seconds. And I can continue this little dotted line across, and we're going to do a little graphing math on this. And we're going to say, look, here I have a line, right? And this distance here, right, is the change in position, which we already decided is x2 minus x1 was 15 meters, right? This difference here, the difference in times between those two points is what we call delta t, and that was t2 minus t1, and that's 3 seconds, right? And if you remember from your algebra class, right, the change in the vertical axis for a line divided by the change in the horizontal, right, is the slope. And so the average velocity So by looking at the slope of position versus time graphs, we can tell a lot about the velocity of a car. And so we'll look at some examples of that. So this is the graph we just looked at, and we said if the change in position is 15 meters and the change in time is 3 seconds, we can say the average velocity is delta x over delta t, which is 5 meters per second. And that's just the slope of this line. In fact, we could pick any 2 points on here and take the slope, and we would get the same ratio, delta x over delta t, because if we change this by a corresponding amount, the delta t will change by a corresponding amount, and the slope along this line will always be the same. Had the car been traveling farther in that time, for example, if the car had gone to 30 meters instead of 25 meters, right, we would have a graph that looked like this. Instead of being at 25 meters here, it would be at 30. right? It would be a steeper graph than the one we had a few minutes ago, right? And our delta x would be 20 meters, and our delta t would still be 3 seconds. And so our V average would be 20 meters divided by 3 seconds, or about 6.7 meters per second instead of 5. Or, for example, if our car after the 4-second mark had only been at the 15-meter mark, our graph would have looked like this, and we would get V average is 5 meters divided by 3 seconds, because it's a 5-meter difference between here and here, right? Or 1.33 meters per second. So this was our original line right here, and you can see as the distance gets greater, the velocity gets greater because the slope gets greater. And so as the car travels a more distance in the same amount of time, the slope is steeper, it's a greater slope, and it's a greater velocity. So now we've decided that the velocity is the slope in a position versus time graph, and of course we can have positive or negative velocities. And so, for example, if my car was at position at t1 equals 1 second, it was at position x1 equals, we'll say, 20 meters, and at t2 equals 5 seconds, it was at x2 equals 0 meters, right? Then I could just draw those points on here, and I can say, well, at 1 second, it's at 20 meters, that's here. At 5 seconds, it's at 0 meters, that's here, right? And I can just draw a line between those two. And just like before, I can identify my change in position, right, and my change in time. This is my x1, because this is where it started, right? And this is my x2. Similarly, this is my t1, and this is my t2, right? And so if I calculate the average velocity for this, I get V average is equal to the change in position divided by the change in time. It's equal to x2 minus x1 over t2 minus t1, and that's just 0, which is my final position in x, minus 20 meters, which is my initial position in x, divided by my final time, which is 5 seconds, minus my initial time, which is 1 second. And so it's minus 20 meters divided by 4 seconds, or minus 5 meters per second. Graphs that have negative slopes correspond to negative average velocities. And so you might think about what a horizontal slope means. Right? Okay. So we just said that the car, our car had started at the 10-meter position, and in 3 seconds it had traveled to the 25-meter position. But really, to calculate the average velocity, all we needed was to know was the fact that it started at the 10-meter position and it ended at the 25-meter position. We didn't really need to know to calculate that average velocity where it was in between, because the average velocity is just x2 minus x1 over t2 minus t1, and to calculate that, we didn't know any of the between points. We didn't need to know them because they don't go into the formula. So in fact, to get an average velocity, all we needed to know was that it started here and it ended here, and it could have done almost anything in between. It could have sat here for 2.5 seconds and then done that, right? Or it could have done this, right? As long as it started here and ended here, over that 3-second interval between t equals 1 second and t equals 4 seconds. And so we're going to look at some graphs of other possibilities for the car getting between these 2 points through different paths, and sort of how they look on a position versus time graph and what we can learn from them. So here's our graph, and what we said was the car started at this position at t equals 1 second. It was at 10 meters, and we call this our x1, and this our t1. And then at 4 seconds, it was at t2, was t2, and that corresponded to 25 meters. And so we had this, and this was our x2 equals, and equals. And we said, originally we said, well, let's just suppose it moved steadily along, right? Of course, as you can probably tell, this is a sports car or a racing car of some kind. And so what it could have done was it could have just sat still for a couple of seconds. It stayed at the 2 meter mark, right? And then zipped along to the 25 meter mark, right? Or it could have done this. It could have gone really fast and gone past the 25 meter mark, and then gone to the 30 meter mark and run back to the 25 meter mark. All three of these cases would have the same average velocity over that 3 second interval because their starting positions and their ending positions were the same. But in between, their velocities were different. And so we're going to look at exploring the velocities of the car at different times along these different paths. So we're going to talk about instantaneous velocity for a minute. So we've already said the average velocity is the change in position over the change in time. And now I'm just going to say, look, our instantaneous velocity is the average velocity over an infinitesimally small time interval. The limit is delta t equals 0. Delta t goes to 0. And so the way to think about this is, for example, if I drive 70 miles to Oklahoma City, my average velocity, if it takes me an hour, is 70 miles in 1 hour, or 70 miles per hour. That's my average velocity. However, I could get pulled over in Yukon, and a highway patrolman would say, here's a ticket for going 90 miles per hour. And I would say, oh no, officer, I'm scheduled to arrive in Oklahoma City at exactly 1 hour after I left Weatherford, and it's a 70-mile trip. And the officer would say, well, I don't really care because your instantaneous velocity, your velocity at this point in time is 90. And you might imagine that no amount of arguing is going to talk him out of that. Highway patrolmen are interested in your instantaneous velocity, and that's the thing that reads on your speedometer. Your car is measuring your velocity, your change of position, over very tiny changes in time, not over large changes in time. And so we're going to look at the instantaneous velocity on a velocity versus time graph now.